Good morning. It's August 27th, and this is your daily brief in science. Here's everything you need to know. A major calving event at Greenland's Petermann Glacier on August 4, 2026, produced a 76.4 square kilometer ice island, the largest floating ice loss from the glacier since 2012 and the biggest Arctic calving event since 2020. Researchers will continue tracking the aftermath with satellite imagery, aerial observations, and tracking data as part of broader efforts to understand calving and retreat processes in Arctic ice shelves. Environment and Climate Change Canada is monitoring the drifting ice island for risks to vessels and offshore infrastructure, noting that thick ice blocks can drift for years and fracture into smaller pieces. The event informs coastal and offshore risk assessments, including potential impacts on shipping routes, and serves as a climate change indicator. Scientists monitor grounding lines to understand ice dynamics, with the loss of the ice tongue expected to speed up glacier ice discharge. Radar interferometry and Sentinel-2 imagery had already revealed fractures and deformations in the Petermann ice tongue, dating back to spring 2026, enabling near real-time crack propagation analysis. Earth-observing satellites have tracked Greenland's ice changes since the 1990s, reinforcing evidence of accelerated ice loss driven by climate change. The discovery involved researchers from the University of Ottawa, University of Stirling, Environment and Climate Change Canada, Lancaster University, and the University of Leeds. Experts warn the Petermann ice tongue remains unstable, with expanding surface cracks potentially triggering two additional calvings of about 97 and 87 square kilometers. The ice island could be up to 150 meters thick and roughly the size of Manhattan, offering a rare chance to study development, transport, and fragmentation of massive Arctic ice masses. Studying ice islands helps illuminate broader polar dynamics, glacier behavior, sea level rise, and marine environments with implications for other polar regions. A new study shows that water droplets picking up charge as they slide down insulating surfaces can trigger coating failure and localized metal corrosion when they discharge on impact. Researchers tracked this two-stage process. First, the slide electrification charges the droplet, then dielectric breakdown on approach leads to a discharge that damages coatings and the underlying metal. The measured charges range roughly from 0.2 to 2 nanocoulombs per droplet, and most of the charge transfer happens at impact, making discharge the trigger for corrosion. AFM imaging reveals hole-like defects in coatings after multiple impacts, with metal damage following. The work, led by Hans-Jürgen Butt at the Max Planck Institute for Polymer Research and published in Nature, examined droplets on surfaces such as windows, plant leaves, and coated metals. Different substrate coating combinations, including Teflon-coated copper, PS on copper and gold, and SiO2 on gold, showed corrosion as a general phenomenon for coatings on metals, not limited to a single material. The findings imply broad relevance for systems with high dielectric inclusions in low dielectric matrices and could apply under rain, ocean spray, inkjet, and electrostatic spraying conditions. While charged rain is not considered hazardous to people, it carries significant material and corrosion implications. The study highlights the importance of science journalism and science communication in conveying these complex interfacial effects. It also raises questions about existing protection strategies across industries, suggesting that routine exposure to charged droplets could pose a widespread corrosion threat and may require re-evaluation of protective measures in infrastructure, pharmaceuticals, petrochemicals, and implants. The researchers propose a two-stage model. 1. Charging of the water drop via slide electrification, and 2. Dielectric breakdown and discharge upon nearing the coated surface that drives coating failure and metal corrosion. Two ancient lineages left their mark on modern genomes, and one of them shows up across populations in Africa, Europe, and Asia. New research using a computer-based method called TRACE identifies a younger ghost lineage that interbred with Homo sapiens in Africa more than 50,000 years ago, and a much older, super-archaic lineage that joined the human genome via Denisovans more than 200,000 years ago. TRACE analyzed more than 500 contemporary genomes and found traces of the younger ghost ancestry across all populations studied, with the younger lineage contributing roughly 0.5% to 1% of living human genomes, similar in scale to Neanderthal DNA. The older lineage appears to have entered the human gene pool through Denisovans in Eurasia, likely via backflow, leaving an older genetic signal in modern humans. While trace can reconstruct missing ancient lineages and identify ghost ancestors, direct fossil DNA remains the strongest evidence for now. Researchers emphasize that human genomes are mosaics of multiple ancestral contributions, and that ancient DNA signals can persist even when the source DNA is unavailable. The findings, published in Science on July 31, 2024, have broad implications for understanding human evolution and adaptations related to disease. Possible candidates for the ghost lineages include Homo heidelbergensis in Africa and Homo erectus in Eurasia, though no DNA from these groups has been recovered yet. The study suggests that additional hidden lineages may exist in humans and other species, as more genomes are analyzed with trace. A leading figure in synthetic biology takes the stage this autumn to map how cells communicate and regulate their functions with precision. Wendell Lim, a UCSF professor and head of the Cell Design Institute, is a pioneer in redesigning biological systems to understand them and endow cells with new capabilities. This year he is the ULF Van Euler Lecturer at Karolinska Institute T, where he will present his latest work to scientists and the public. Lim has helped establish synthetic biology as a field focused on understanding cellular function and enabling new cellular capabilities, and he has led major research centers in synthetic biology and cell therapy with international recognition. His research highlights programmable immune cells, including synthetic T cells, designed to recognize diseased tissue and activate exactly when needed for safer, more effective therapies. The overarching goal is to develop safer and more effective cell therapies for cancer, autoimmune diseases, and degenerative diseases, potentially advancing future treatments. A major focus is developing programmable immune cells that can recognize diseased tissue and make precise activation decisions for safer, more effective therapies. Lim will deliver the Ulf von Euler Lecture on October 9, 2026 at 2:15 p.m. in Stockholm's Eva and Georg Klein Lecture Hall, Biomedicum. The event at Karolinska Institute T will share his findings with both scientists and the broader public, and is part of autumn programming honoring his work. Lim's leadership at the Cell Design Institute in the Bay Area underscores his role in advancing synthetic biology, from theory to practical cellular capabilities. An international team from the University of Tokyo has demonstrated an atomic-scale double-slit effect using a focused electron probe to read out vibrations of neighboring silicon atoms, effectively visualizing phonon-driven lattice dynamics at the scale of a single chemical bond. The experiment treats two adjacent silicon atomic columns, spaced 136 picometers apart, as a natural double slit and observes interference fringes that reveal coordinated vibrations between the neighboring atoms. This approach points toward ultra-atomic resolution electron microscopy that could surpass traditional methods and inform heat dissipation design and energy efficiency in semiconductor materials. By watching how the fringe patterns shift, researchers can infer the direction and synchronization of atomic vibrations and identify regions where heat accumulates or travels less readily. The work is part of the Shibata Ultra-Atomic Resolution Electron Microscopy Project and was conducted with Thomas Susi of the University of Vienna, with results published in Nature on August 19, 2026. The study offers a new method for measuring phonons and bonding strength at the atomic level, potentially guiding the engineering of heat conduction in materials and semiconductors. The findings provide a direct link between fringe behavior and atomic-scale energy flow, offering a tool to map phonon activity in real space. In essence, the technique translates vibrational dynamics into observable interference patterns, enabling insights into lattice heat transport at the scale of individual bonds. The research could influence future design of materials where efficient heat dissipation is critical, such as advanced semiconductors and nanoelectronic devices. This has been your daily brief in science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. Tune in tomorrow. We'll be back with everything you need to know.